Hello, my name is Dave Montgomery. I'm a third year PhD student in the Applied Math and Statistics department here at Mines. Today, I'm going to present on the work I've been doing with my advisor, Dr. Corinne Liederman, on modeling clot formation under flow and extravascular injuries. When a blood vessel is injured, platelets aggregate at the injury site and couple to a complex system of biochemical reactions to form a stable blood clot. Computational models of intravascular clot formation have been developed to study injuries where blood does not leak from an injured vessel. However, we want a model that captures the dynamics of extravascular clotting, one that allows blood to continue flowing through the blood vessel while a clot forms outside the vessel. Modeling extravascular injuries, like the one animated on this slide, requires solving numerous equations in geometries much more complicated than a simple rectangle. The first model our group came up with to simulate extravascular flow is the H-shaped domain seen here. In the lab, our collaborators pump blood into the right blood channel, while a similar fluid enters the left wash channel at a higher flow rate. The difference in flow rates creates a pressure drop between the blood and wash channel, causing blood to flow through the injury channel. The injury channel is coated with combinations of collagen for platelets to adhere to and tissue factor to initiate coagulation. Coagulation only occurs in the injury channel, allowing continuous blood flow through the blood channel, much like that of a blood vessel after it has been cut. My research thus far has been focused on the fluid motion in the H domain. Our goal is that once we know what the fluid is doing in the H, we will be able to build upon our model and track platelet aggregation. Today, I will present on our preliminary results for the fluid motion in the H domain. The fluid flow is governed by the 2D incompressible Navier-Stokes equations. U represents the fluid velocity and P the pressure. Rho is the density of the fluid and mu is the viscosity. The extravascular injury domain, or what I will often refer to as the H domain, is discretized using a domain-conforming mesh in order to limit the number of unknowns in the problem. Once the mesh is created, the spatial derivatives are discretized using a finite volume method, which converts the original PDE into an integral equation. The advantage of the finite volume method is that the integral equation is of conservative form, meaning that quantities such as mass and momentum are conserved on each finite volume cell. The integrals are then approximated using quadrature rules and various interpolation schemes. To ensure incompressibility, the nonlinear terms are interpolated so that the continuity equation is satisfied on each pressure cell. After spatial discretization, a Chorin-like projection method is used to march forward in time. The method decomposes the incompressible velocity field, un plus 1, into the sum of a smooth but not necessarily incompressible velocity field, u star, and the gradient of a scalar field, p star. The projection method decouples pressure from velocity by projecting onto the space of all smooth velocity fields, including compressible velocity fields. At each time step, we solve the momentum equation for a predicted velocity u star using pressure from the previous time step. U star is then used in a Poisson equation for an intermediate variable p star. To recover an incompressible velocity field, an update is made at the end of each time step, coupling the current velocity with the current pressure. Note that the semi-implicit discretization of the momentum equation allows us to move the nonlinear terms to the right-hand side. Therefore, to solve the momentum equation at each time step for u star, we solve two large linear systems. Additionally, the Poisson equation is also linear, so at each time step, we must solve three linear systems. The fact that we solve three linear systems in each time step is why we chose to use a domain-conforming mesh. In this slide, we are using MATLAB's SPI function to highlight the location of non-zero entries in the coefficient matrix used to solve the x component of the momentum equation. Notice how the spacing between the coefficients changes as we progress through the H domain. Again, at each time step, we solve three linear systems whose matrices look like the one we see here. We first tested the spatial accuracy of our scheme by using a manufactured solution of sines and cosines with Dirichlet boundary conditions. As expected, we observed second order spatial accuracy. This can be seen in the right figure where the errors in U, V, and P are decreasing as the number of spatial points in our simulation increases. Next, we tested the temporal accuracy by fixing the spatial discretization and running simulations with smaller and smaller time steps delta t. Again, we observed second order accuracy, which can be seen in the right figure where the errors decrease as delta t decreases. Once we knew that the finite volume method was second order accurate on a standard test problem, we began focusing on how to validate our numerical scheme with flow through the H. Schumann et al. Used a hydraulic circuit model to estimate flow rates and pressure throughout the domain. The hydraulic circuit model is analogous to Ohm's law, but instead of V equals IR, the hydraulic circuit is delta P equals QR, where delta P is the difference between two pressure values, Q is the flow rate, and R is the hydraulic resistance from the channel geometry. Mass is conserved via the sum of the inlet and outlet flow rates. Solving the resulting linear system provides boundary conditions for velocity and helps us validate our numerical results. We updated the boundary conditions in our model so that we could prescribe the flow rates at the inlets of the H and a zero gradient at the outlets. The model is initialized using a stagnant velocity field and run until it reaches a steady state. Overall, we get good agreement with the hydraulic circuit analysis, most notably in the injury channel, where we are most concerned. The figure on the left at the bottom of the screen is a bright field image of whole blood in the extravascular injury device taken from the 2017 Schumann et al. Paper. The figure on the right is a plot of the streamlines from our numerical model. Our last slide is a heat map of the velocity and pressure. The leftmost plot is the x component of the velocity field, showing a nearly fully developed flow through the injury channel that cascades from the blood channel and out into the wash channel. The middle plot is the y component of the velocity field, showing nearly fully developed flow in the wash and blood channels. Notice the darker blue color at the bottom of the wash channel, signaling an increasing flow rate after the injury channel deposits fluid into the wash channel. Similarly, you can see a higher flow rate at the top of the blood channel that decreases after losing some fluid in the injury channel. On the right, we see that pressure is varying linearly with an obvious pressure drop from the blood to wash channel. Overall, we are happy with these initial results, and we are beginning to add various terms to account for frictional resistance in the fluid due to the presence of bound platelets. Moving forward, I am working on adding in a Darcy term in order to simulate the platelets building up in the injury channel. I am also working on parallelizing my code for faster simulation times. I want to thank my advisor, Dr. Corinne Liederman, for her help and guidance, the National Institute of Health for funding this research, and you, the viewer, for watching this presentation. Feel free to reach out with any questions or comments by emailing me at dmontgomery@mines.edu. Have a great day, and thanks for watching.